Hello everyone, welcome to LearnOverflow. In this video, we'll discuss another LeetCode problem that is the pseudo palindromic paths in binary tree. This is a medium level problem. I don't understand what this question is asking us to do and in what way we can actually solve this question. So before moving on, if you haven't subscribed to this channel, make sure to subscribe to LearnOverflow for regular LeetCode videos like this. The question says we are given a binary tree where the node value are digits from 1 to 9. Okay, so this is the node value from 1 to 9. Now, what further it says a path in the binary tree is said to be pseudo palindromic if at least one permutation of the node value in the path is palindromic. Okay, further it says return the number of pseudopalindromic paths going from root node to the leaf node. So we just need to return the number. Okay, now let's understand as an example. As an example, you see like here we have an binary tree with us, and in this a path like 233. There's actually three paths 233 and then 231 and then 211, right? So there's like three paths. So in this you find like 233 and 231 are pseudo palindromic. Why is it so? Is it's simply because if like there's like 2 3 3, right? You can rearrange them into something like 3 2 3, right? So this becomes palindromic. And then when you have 2 1 1 in your another path, you can rearrange that into like 1 2 1. So that's a palindrome. So that's the question is asking us to do, to just count this kind of paths we have where from root to like from the root to the leaf we will traverse and we'll see what are the paths, like what are the values we have, and is in any way if it's reorder is palindromal, like reorder is palindromal, right? So that's the question. Now if you think on it clearly, so there will be two questions actually involved in it. One, to simply traverse the like one question would be to traverse from the root till the leaf. Okay, just to traverse. So like first thing is to build the tree, right? That uh, all the paths should be traversed by us, starting from the root to each of the tree, like each of the leaves. So for that, how we can do that? We can have a like whenever we are going from root to leaf, then it's better to go with the breadth. It's not better to go with the breadth first search. It's better to go with the depth first search. You keep checking the depth, like start from the root, then keep checking the depth unless you reach the end, and then reverse back to check for the other path. So that's the way we follow for uh, uh, this kind of operation where you need to reach the relief fast. Okay. So in that case, we will use a depth first search operation, and in depth first search, we'll prefer pre-order traversal, like the root, then the left, okay, and then the right. So root, then left. So followed by that, we'll again follow the left of it, and then we again follow the left if there is. So we follow the left, and after the left, we'll go back to the root and then move to the right. And similarly, we'll go back and then go back to the root and move to its right. So this is the format that happens. Okay, in depth first search, you are aware of it, like pre-order depth first search way. Okay, so that's what we will be going ahead with, and then there is another part of this question. Another part is like for each of the root to leaf path we find, we need to check if the path is a palindrome or not. This is the most important part because depth first search is common to the many questions, right? So how do you check for this path now? You might be thinking that you have a way of traversing through this. Okay, how you might be traversing through this? You will be simply going ahead with I mean, you simply keep a take an array, okay, and in that you keep on storing the values. Like if it is it's mentioned that the digits are from 1 to 9, so you can keep a count of the digits. Like say zero, like in this 1 2 3. I'm considering zero is something over here, fine. So 1 2 3, and each of the digits you keep on incrementing the count. So that's what you can do, right? You can keep incrementing the count and find the values. But what is the exact thing we are trying to do? for a like number or for a group of numbers being palindrome, we need to see that there should be at most one digit who has a frequency of one, like who has an odd frequency. Fine, not one specific, who has an odd frequency. Like there should be one digit who has an odd frequency. What I mean, say there's a number like 2, 3, then 2, then 3, then 2. If a number, if a path comes out to be something like this, then is it a palindrome? Yes, it's a palindrome. Why? The idea is, why is it a palindrome? The main thing is you find this number 2. Number 2 is actually there 3 times, and number 3 is actually there 2 times, right? That's the count of those numbers. In that, you find if a particular number is there odd number of times, and all other numbers in it, say there's a 4 here, fine, and there's a 4. I'm repeating 4 both sides, right? So if all other numbers are like even number of times, okay, so if that is the case, we are sure that this is the palindrome. Like we don't need to rearrange them and find the palindromic sequence, right? We are simply sure, like if one number is there who only a single number is there whose frequency is odd, and rest all other numbers has a frequency of even, then we know it's a palindrome. Fine. So that exactly we know out here. So how we can find it out, like that's what we want to find out. So in that case, what you can do, you can simply keep a like array like this of like 10 elements, and like 10 elements like till 9. Fine. It will be there 0 to 9, so that's 10 elements, and keep on increasing the values, like the count of these values as I'm showing here. So you can do that, and once you reach the leaf of that, and then like go through the whole array. The array is order of like 10 elements are only there, and find out if there are multiple odd numbers are there or not. Simplifying odd numbers, like mod 2 double equals 0 gives an odd number or not, right? So you can do that, but that won't be a most visible way. See, there can be other ways also you can do that. You can take a hash map and take your numbers, take your particular numbers and map it to the its count. Fine, you can do a hash map kind of formulation. Also, like why this is not the most good solution, because it's using a lot of memory. See, in the first case, it's using a total of like total of 10 as memory spaces, right? But that's huge. You don't need all those. If there are small elements, it's like you can 1 2 3. If there is like 1 2 1, then you need only 2 spaces, right? So that's wastage of lot of memory. And then for hash map you can do that, but again and again you were putting into the hash map and getting the value, incrementing the value can be a like if for larger trees this can be a bigger issue, right? So we have to find out something that can solve our question in this, okay, that can be a feasible solution in this. So what we actually do over here is use a simple like trick, that is we keep on computing the parity on the fly. Okay, how we do that? Using bitwise operator. What does that mean? I'll show you in a simple way. So we take a variable called say we are taking a variable path. Fine. So that's a variable we have. Now this variable is initially obviously initially 0. So once this variable is 0, so we know that it will be something like if I just care for a binary, so it will be something like this. Fine, I took 6 digits. Doesn't matter, but yeah, let's say 8. Okay, so this is the path variable we have. Okay, so what we do? Say we found a number. We found a number as if like the node value. Okay, node value. Say we found x, and if we found x and say we found 1 over here. Right? Let's take a easier number and let's understand. Node value is 1. So if node value is 1, that simply means 0 0 0 0 0 0 0 and 1. So that's what x is. And what we do exactly over here, we store this value on that path like we'll do a operation like path, then XOR of one left shift X. Okay, we'll keep repeating this operation again and again and again with the storage value. See how it works. So once you do one left shift X, okay, once we do one left shift X, so X is one, okay, and we are doing a left shift of one bit. So once we do this one left shift X, so one left shift X, fine. If this is our case, so it results in 0 0 0 0 0 0 1 0. That's a left shift happened, fine. That's one left shift X. Now do what XOR operation of this two, okay, XOR operation of this two. So if you do a XOR operation of this two, XOR works in a way that if both the bits are different, it results in 1. If both the bits are equal, it results in 0. So this is the XOR operation works. So you're doing XOR, so say 0 0 0 0 like 0, and here 1. So what we are getting? 1, fine. And similarly the rest is 0. Okay, so that's we have over here, fine. Now say we after the first occurrence of 1, like this value 1, this X is the value, original value, okay. So after the first occurrence of 1, we get a value we find our path value, well, to something like this. And say after the second occurrence of 1, we again perform the same operation as in we left shift X by 1, okay, and then do a XOR with path. Okay, now it's something to note here. We have actually stored the path to be equal to path XOR this. So this particular value is our current path right now. Okay, so if this particular value is current path right now, and we want to XOR with this value again, one left shift X. So what we mean? We mean this path. Say I say write P XOR one left shift X. So this is what we did initially in the first step. And in the next step, when we find 1 again, so again we want to do a XOR of one left shift X. Okay, like the number of time we keep finding the value, we keep finding the numbers we have, we'll keep doing the XOR. So how this is beneficial? So this is the previous answer we find, and we want to XOR it against with one left shift X. So see what we find in this case. So for 0 0 0 1 1, as I said, XOR results in 1, only both the bits are different, but here both the bits are equal, so we find a 0 and the rest are all 0, fine. So that's what you get here. So what it means, or what you gain out of here, it simply means that once we are see if it results in what manner, we have 1, so this is the 0th place, this is the 1, this is the 2, this is the 3rd place, this is the 4th place, right? So this way it goes. When you are converting from binary to decimal, you use this kind of formation 2 to the power 0 into this, like then 2 to the power 1, 2 to the power 2. This is the formation we use, right? But so that's what we need to remember. Now how this actually works in our case, this is storing 1, like a bit is shown as 1 only if that bit is odd number of times, okay, and it is storing 0 when the bit is even number of times. So again if you do a XOR of one left shift X with the previous value we have over here, then we will find, see, this is actually doing the XOR with the initial path value, right? So that's what we are trying to do. Like if we are left shifting with X, that simply works in a manner that that particular bit will be highlighted if it's an odd number, or it will be set to 0 if it's an even number. So this is the idea. This is the way we actually keep this value stored. And so what's the profit of doing this? Like doing this simple formulation, we are storing it in a single variable. We are not storing it in an array or in a hash map or in a hash set or something like that. We are not doing that huge memory cost are going on. Okay, we are reducing our memory cost and at the same time our complexity as well. because once we have an array, we need to traverse with the array to find out which value has resolved. But if we just take if this path is 0 or not, if this path is 0 or if this path is 1, like which if only one value has a 1 or multiple values has a 1, that we can directly check using power of 2, right? Check for the power of 2 result in that way. So that's the idea, that's the way we check it. Fine. Now as I said, I need to explain that power of 2 part again, because what the idea was previously, if you think, we have did a question on power of 2, and that's there on my channel there also. So I was just writing something related to power of 2 below over here. Now, what happens if we are trying to check? If you are trying to check if these numbers are only single value is 1 or not, then how we check that? We need to check whether there are multiple ones or not, right? If there are multiple ones, it's a false. We don't have that's not a palindromic path, right? Pseudo palindromic path. But if there is single one, that means it's pseudo palindromic path, right? For that, power of 2 comes into play. Power of 2 is like how we do that. We have a value x and we do a AND of x minus 1, right? So we do this, and if this becomes 0, that means it's a power of 2. Okay. Say we have a value of 4. 4 is the power of 2. 4 is like 100, right? I'm not writing the all the 8 bits, but see, that's 4 is 100. What is 4 minus 1? That's 3. 3 is 0, 1, 1. That's 3, right? And we do an AND of this. AND of this is 0, 1, 0, 0, 1, 0, and 0, 1, 0. And see, this results in 0, right? So in 4, we have only one single bit that's highlighted, like one single bit, that 1, right? So like in our case, we are counting this value storing the path of which value is 1 or not, right? So if only one single bit is highlighted, it will result in 0. Fine. It will result simple 0. That is a path we are looking for. But what if it's the reverse case? It's a reverse case, like there are multiple. Let me erase this the whole page off, right? I'll just explain this small part again. Say I was saying x and x minus 1. This should be 0, right? So that's the way we found out if there are multiple values having a single 1 or not. Say we have a single value like 1, 1, 0. Fine. If you see the binary, it's a 6. So don't convert this to binary, because this is the path value. So this is storing the all the values of value that are there in our path. Okay. So if that is 1, 1, 0, that means there is one the odd number of 1, there is odd number of 2 as well. So that's the question is like that's what it is storing over here. So if we apply this kind of power of 2 formulation, see what would happen. So x and x minus 1. What is x minus 1? X minus 1 will be 1, 0 is there. So we minus 1 with it. So it's like 1, 0, 1. Okay. 1, 0, and 1. Fine. That's a minus 1. And if you do an AND of it, see, it will result in 1, 0, 0. This is not equal to 0. And you find that there are multiple values, right? There are multiple values uh, which are actually 1 in our path. That means there are multiple values which are odd in number in our path. Okay, and that's the check we are doing. Okay, it should be like there should be at least one, like at most one. You may ask, what if there are all the values are 0? So what if there are all the values are 0? Fine, all the values is 0. And what is subtract 1 from it? Nothing. It results in all the values is 0, right? So all the values are 0 minus 1 is doing the same thing, but that bit like the most significant bit, the sign changes. That's not the idea. So this results in 0 as well, right? So all the values are 0. What does this practically mean? This practically mean all the like in our particular path, all the numbers we have all are in even, right? Can it happen like if you are checking for a palindrome, all the numbers are even? Yes, definitely can happen. 2, 3, 2, 2, 3, 2. Is it not a palindrome? This is a palindrome, right? So we want to check if there's a at most one, like if there's at most one place is odd, like at the maximum one place can be odd, minimum no places can be odd. So minimum no places can be odd. This can be a case for that. Maximum one places can be odd. Just erase of 1, 2 out here. The maximum one place is odd. That's the case. That can be a case. So this is the two cases we need to follow. So this is a short and simple code we have. Fine. This is a pretty much fast solution on 30 milliseconds, but I think this should go down a bit, but it's pretty fast. So let's see what we did actually. We used another compute function. So this is for our DFS traversal. Okay, this is the first step for us. Now, in this, so we simply passed it. So we passed the value 0. So this is the initial path value. As I said, the path we are choosing. The path value is the one that was doing like storing the values or storing each of the digit count. Okay. Now, further, the first thing we check if a root is null, return. That's the preliminary check. In case our if the path like we apply this formulation, what we are just storing path XOR one left shift root dot val. One left shift root dot val will simply, as we are discussing, it will simply increment the count and will store if a number is like that root dot val is even numbers, like even number of time or odd number. It will store that part. So this is what the path XOR one left shift root dot val is doing, right? And then we are checking if our left is null and our right is null. If our both left and right is null, then we, so if our both left and right is null, that simply means we are at the bottommost value, or we are the left node. Okay. So in that, we'll first check if the path is 0. If path is by default 0, there's no need to check for the power of 2 and all those, right? Path is by default 0, incremental is 1. Or if path is not 0, that means there's some kind of one like some bit is marked as 1, right? Maybe one bit, maybe multiple bits are marked as 1. So if single bit is marked as 1, this will result in 0. If multiple bit is marked as 1, this will not result in 0. So if single bit marked as 1, we increment our result. Result being the final result, finding out how many pseudo paths. These are calculating the total number of paths. And once we have checked like both root and root left and right are null, so we are simply returning out here because there's no point going further in depth, right? Then what further we do, we move to its left or move to its right. So this move to its left and move to its right, this work only if both the left and right are not null. Maybe one is null, the other is not null. So this statement works in that purpose. Okay. This is the whole working of that. See, only we are using an order of one space. Why order of one? Because this is the only extra path variable that we are using, right? We are not using additional variables to just store or additional value to store, right? And if you look at what is the complexity? Complexity is like we are traversing through the height of the tree, right? We are traversing through the height. So what is the exact complexity? Complexity is like order of height, right? So the order of height of the tree is the complexity we have over here. That's the time complexity. Because this is simple DFS traversal, nothing happens like this. Compute function is there, and we are, if it is both are null, like if it's leaf node, we are returning. Else, we are going into the depth of that root. Okay, till we find the root leaf. So there's a height of the tree, is the complexity we have here. So if I'll just run it once again, I guess this may reduce or may not. Yeah, it somehow reduce. Anyways, so this is the this LeetCode online judge is confused at some time. with how much second they wanted. Anyways, it doesn't matter. So this is more or less the idea and the approach we take to solve this question. And so thank you all for watching this video, and make sure to comment down if you have any doubts related to this. I'll be happy to help you out in the comments as well. And also like this video and subscribe to this channel for regular LeetCode videos like this. So thank you all. Hope to see you soon in my next video as well. Thank you.